All right, good afternoon. Let's continue the lecture after a break, a week of break. First of all, the midterm grades have been entered on Canvas, and the average of the class is 73.5%, so that's not too bad. Okay. But however, when we mark the exam, and we do notice TA marked one question each, and I marked one question. Okay. And we do notice that there are a lot of mistakes that are not supposed to happen. And the nature of this kind of question of this class is always you make a mistake from the first step, and then it will carry through for the rest of the question. So unfortunately, for example, if you get the fourth wrong from the beginning, then there's definitely wrong for the for the final results. So you have to be very careful in your first few steps, and also about the fundamentals, right? Like how do you get the force, reaction force, free body diagram, and those are prerequisites not supposed from this course. Okay. So I don't have your exam paper here today, but if you want, you can come to my office to pick them up. I can bring them here to next lecture, right? But it'll take some time to distribute them. But anyway, so if you can't wait, please come to my office to pick them up. Okay. And also, by the way, next week we're going to have our quiz number 2. Okay. So we're supposed to have maybe about 4 or 5 quizzes. So there's going to be a second quiz. Posted on the Canvas. But I noticed that some student emailed me about some information that I already posted on Canvas. So I wonder if whether you're looking at the announcement section or not, right? So that part, so you have to do some due diligence yourself. Okay, so let's continue on the lecture here. So we started on introduction to gears. So let's finish this part. Continue to the introduction. We'll finish that. Okay. Yeah. So we talked about the specialty about the gear is because the profile of the gear is involute profile, and we also talked about a lot of terminologies associated with the gear. This week tutorial, the TA will help you to go through an exercise which basically is to create a gear, spur gear, using SolidWorks. So this way you can actually familiar yourself with all the different type of terminologies associated with the gear. Okay? Yeah. The other thing is let's continue here is let's talk about the point of contact, line of action, and pressure angle. Okay. Now from this diagram here, it's a little bit hard to tell, but there are 2 red circles. Okay. So these 2 red circles are basically the pitch circle, and this line in here is called the line of action, if you recall that. And this line of action is tangent to the 2 blue circles at here, which are the so-called the base circle. Okay. So base circle are the circle where your involute profile will be generated. Right. So basically, involute curve will be generated based on this blue circle at here, and the angle between the line of action, okay, and the horizontal line, okay, which sometimes we call the pitch line here, give you the pressure angle. Basically, this angle here is the pressure angle. Okay. So geometrically, the pressure angle could be actually any numbers. So if you have the base circle here, you can generate an involute profile, okay, from the base circle. Okay. It can be as long as you want, okay, and you can use any pressure angle, okay, along this basically involute. But in gear industry, there are essentially 3 different pressure angle you use: 14.5, 20, and 25. Okay, so basically that dictates how much of basically involute profile you use based on this pressure angle. Okay, so this is the pressure angle, and the nature pressure angle essentially give you a direction where the action-reaction force, okay, goes along this direction. Okay. So you have a pinion drive the gear. So the force from the pinion to the gear, right, will be this direction, and the reaction force from the gear to the pinion will be the opposite direction, but still along the same pressure line. Okay? Yeah. Now the other thing is line of action point of contact means where the contact point is between two pair of gear teeth. Okay? The nature of the involute guarantees that the point of contact will be always along this line of action. So basically this point here, as the gear moves, it will always be along this line of action. So I can show you a little bit animation in here. So this is a software. Unfortunately, it's not free, but anyway, so there's this pinion and a gear here. So you can observe carefully when the pinion is driving the gear. This contact point will always be along this line of action here. Okay, should be this way here. So as it moves, okay, that point of contact is always along that line of action. Okay. So that's basically the nature of involute profile. Guarantees that the contact point will always be on that line of action. Okay, so this is basically the parts of this one here. Okay, another concept is called contact ratio. Okay. So when you design for a gear, and bear in mind of this important parameter, the contact ratio. The meaning of the contact ratio using symbol MC basically says it's a measure of the average number of teeth that are in contact. So what does that mean is if you look at this case, right, in this case we have diametric pitch 10, number of teeth 13 for the pinion, gear is 28. So as you can see, okay, right now at this moment, how many pair of teeth in contact? So there's definitely these two pairs here and these two pair. So there's basically more than one pair of gear tooths are in contact, right? So that's the number representing contact ratio. Generally, you want this number to be more than 1.2. So if it's exactly at 1, so basically means you only have one pair of gear teeth are in contact, okay, always. Okay. So how do we quantify this thing in here? Okay. Before we give you the formula here, and the other thing I think you also need to maybe I'll talk about this next. Okay. Yeah. Well, let's look at this. Maybe let's look at this for now. Okay. Look at the fact here. There's an important point in here is the intersection point between this big circle at here and the pressure line, okay, line of action. So this intersection point. Do you remember what this circle is called? Addendum circle. Excellent. Addendum circle is the most outside circle for a gear. Okay, and addendum circle basically represents what? Represents the ending of this envelope profile. Okay, that's basically where your gear tooth profile ends at the addendum circle. So the intersection between the addendum circle and the line of action, okay, so which is the blue dot at here, that represents basically either the beginning or the ending contact points between these two gears, the pinion and the gear. So you can take a look at carefully at here. So for example, right, if you move at this moment, and that's where they start to disengage. And this blue dot here, right, will be the points when they start to engage at here. Okay. So if you look at this point, there, yeah. Anyway, yeah, the one is still moving. Why doesn't pause here? Yeah, it's supposed to pause. I don't know why it's paused. So that's the nature of the engaging and the disengaged points, are the intersection between the addendum circle and the line of action, right? So this is the intersection between this addendum circle and this line of action. And this point is between the other addendum circle, the gear's addendum circle, and the line of action. Okay? Yeah. So these 2 points determines the engaging point and disengaged point. Okay. So what is contact? How do I measure the contact ratio? Right. Okay. So this diagram here more or less shows you what I said. These points A and the points B are the engaging and disengaging points. Okay. Then from A to B, the distance is defined as the contact length, LAB. Okay. The other important parameter over here is, okay, from A to B, and then you have this so-called arc of approach and arc of recess, QA, QR. And when you add the 2 arc lengths together, you get the so-called arc of action, QT. Okay? Yeah. So this QT at here, basically MC is defined as QT over small p. Okay? Small p is the circular pitch. So circular pitch is an important parameter, right? When you design for gear, you have a diametral pitch, you have a circular pitch, they're related. Right? So MC is defined as basically this QT over the circular pitch. Okay. So I think I have the definition at the bottom here. So QT is the circular pitch along the pitch circle, okay, from here to here. Okay. You can calculate this line of action LAB using this formula. Okay. Without derivation, you can look at my lecture notes. I do actually have a detailed derivation of how LAB is derived. It does require a little bit geometric background. Okay. So this is the LAB, which is related to, for example, the radius of pinion, the radius of pinion addendum circle, radius of gears addendum circle, radius of base circle pinion, and also base circle radius of the gear. Right? And C is the center-to-center distance, and phi is the pressure angle. So you can calculate LAB using those parameters, and we can prove that the contact ratio, okay, is equivalently you can calculate the contact ratio using LAB over PB, and PB here is this circular pitch along the base circle. Okay. So those formulas, you don't have to always memorize these things. Later I'll give you a template which have already coded all the formula into the template. But it's good that you know, when you look at the formula for the cell, so then you know where they are from, right? Okay? Yeah. So this is a contact ratio, all right? And when you design for gear, you can list the contact ratio, and you can see, you know, what you try to avoid is that 1, right? As I said, suggested to be above 1.2. The other concept is called interference. Okay, interference. So what is interference then, right? So let's go back to this, maybe this animation in here. Okay. Now I'm gonna increase the number of T's a little bit, okay, to 16. Okay. So now let's observe one thing in here. Okay. So look at this line of action, okay, which is tangent to the 2 base circle. Okay. This is the base circle for the gear, and this is the base circle for the pinion. Okay. And the tangent point one is over here, and the other is over here. Okay, so that's basically the nature of the line of action, which is tangent to the two base circles. Okay. And now the two blue dots, as you recall, which refer to the starting and ending engaging points, right? Right now, the two blue dots, they are well within that two tangent points. Okay, two tangent points. And we call this is the situation that you will not have interference, because when the two blue dots are within the two tangent points, whenever the two gear tooth are engaged with each other, the engaging points are always on the involute profile, which is exactly what we want. You want involute engage involute. You don't want involute to engage non-involute. Okay? So when does that happen? When involute engage non-involute? If I reduce this one to certain number, say 12, okay? Now if you watch carefully, this blue dots right now goes to where? Goes to outside this tangent point now. Okay? So at certain points, somewhere like around here. So the engaging maybe a little bit more than this. Yeah. Okay, so let's say around here. This part, the blue one, is still involute. But the brown color here, okay, technically it is not going to be involute anymore, because you see this is the base circle. Anywhere below the base circle is actually not involute profile. So when you draw gear, anywhere below the blue circle, you actually just draw a straight line all the way to the radius. So basically what's going to happen at this location is you have an involute portion of the curve engaged with a straight line, which is non-involute portion of the curve. So that's what we call interference. You all have gone to dentist, and you probably not all of you, but anyway, so you have probably done a filling of your teeth, right? What's the last step the dentist will do to you? They'll put a blue color of paper and then ask you to grind it, and they look at the color and then they grind it a little more, right? And ask you to grind your teeth, see if you feel comfortable or not, okay? Until you feel comfortable. So when you're not feeling comfortable, exactly what happens there is interference. Okay? So part of your involutes is engaged with non-involute. So that's called interference. So what happens when you have interference? So the involute portion will always try to dig into this non-involute portion. Okay? And as time goes on, basically you have a grinding noise, or you have uncomfortable, right, feelings. Okay? That's exactly basically when you design for gear, you need to avoid this interference. Like in this case study here, interference is avoided by a technique called undercut. So this portion of gear teeth, this portion, okay, is actually already being undercut. So technically it's a straight line all the way down here, but it's being undercut a little portion at here to avoid that interference. Okay? Yeah. So interference is important because you have to avoid it, but you have to know under what situation that you need to avoid interference, right? So there are a number of things that you have to be very careful, essentially, when you do the calculation for the gear, which is essentially what you're trying to avoid the interference. Okay. This is the same demonstration at here, but I'm going to write down a few formulas so that you know that when you should avoid interference. Okay. If gear ratio is 1:1, okay, then you should know that the smallest number of t's for pinning, okay, is this this formula here. In this formula, there are two parameters. One parameter is the pressure angle phi. Okay. The other parameter is this parameter k added here. Okay. Yeah. So k, you take it as 1 for full teeth. Okay. There's another type of teeth is called stub teeth. So stub teeth is a little bit shorter teeth. Full teeth is the standard size of a teeth. For stub teeth, I can't remember. For stub teeth, K should be 0.8. I can't find it anymore. Okay, you can check the notes. There's another one here for the stub teeth. Okay. So if I plug in, for example, right? So you can plug in a phi equal to any number 20 degree, and then you can plug in k equal to 1 into that. Then you'll be able to calculate the NP at here, which will be 13. Okay. So this is for gear ratio 1:1. And of course, we typically deal with a gear ratio more than 1:1, of course. So if our gear ratio is defined as the number of gear teeth number over the number of pinion teeth number, and of course typically is greater than 1, and then we have a different type of formula now. The smallest number of teeth for pinning. So we're talking about here is the smallest one without interference. Okay. And this time the formula is changed to so let's just use M here instead of mg. Okay, so change to this one here. So it's different from that, but this one includes that formula, right? So this is more of a particular one from here. Okay, if you set m equal to 1, you should get the same thing. And the largest number of teeth for gear, so not just this smallest number of teeth for pinning, but also the largest number of teeth for gear, okay, is ng equal to np square sine phi square minus 4k square okay, 2np sine phi square. Okay. So these two formula, you use them together. What's the smallest one and what's the largest number? Okay, to avoid interference. So let's see a few examples here. For example, if you use pressure angle 20 degree, okay, so if you choose NP equal to 13, then you get NG equal to 16. So you plug NP over here, you get NG equal to 16. So basically means what? When you choose the number of pinion as 13, then the largest number of teeth for gear is 16. Okay? So in this case, your largest gear ratio is 16 over 13. Okay. Now if you choose NP equal to 14, then you get a different number, 16, right? So this is essentially what's in our table in the textbook, in the lecture notes, also in the textbook. And you'll have this table here. 14 to 26, 16, 101, okay? And when the pinion teeth is 18, you actually can choose the largest number of teeth for the gear can be infinite. So basically means when your pinion number is 18, your gear ratio can be as many as possible. Okay, so you're not going to have any interference at all, essentially. Okay, yeah. But there's always trade-off, right? You know, when you have the more number of teeth for a gear, then it's getting more expensive. So it's always a trade-off. Okay. Okay. So what would be the possible way of avoiding this interference thing, right? Okay. So there are a couple ways you can do that. Okay. So I'll just show you the picture here. Okay. Since interference happens only when the involute portion is in contact with the non-involute portion, then if you can have as much of involute curve for the tooth profile, then the less chance you will have interference. So this is the effect of pressure angle. As you have larger pressure angle, the base circle will become smaller. That comes from this formula. So the base circle radius equal to the pitch circle radius times cosine pressure angle. So the bigger phi is, the smaller IB is. As you can see, basically when you have a 25, then you have more involute portion than 20 and 14 and a half, right? So basically bigger pressure angle will have a less chance of interference. Okay? Yeah. And then the other thing is, later we're going to come back to this. You also want to try to avoid too few number of teeth. Okay, when n is very small, okay, then the diametral pitch will be small. If diametral pitch is small, then the addendum A equal to 1 over capital P will be too big. So addendum, if you remember, that referred to the length from addendum circle to the pitch circle, right? So what does A is too big mean? A is too big basically means it's like your teeth is too big, right? So it's like sticking out a very long teeth, okay, and which is not that good, okay. Yeah. But it's good for some other effect though, okay. Yeah. So we'll look at this effect later in more detail when we do the gear design. Okay. But these are the two things that you can try to use, okay, to avoid interference. All right, so that's some of the terminology. Let's continue on the introduction in here. And now I'm going to look at gear train and gear forces. Okay. So let's look at the gear train and gear forces. So first, very simple concept, gear ratio R. Okay. Now when we talk about gear ratio R, you got to understand that under different contexts, sometimes people use a differently for gear ratio R. Okay, but in essence, essentially, you use gear ratio R to calculate gear ratio R using either the angular velocity ratio or use the ratio between the number of teeth on the two gears or the radius, the ratio of the radius of the two gears. Okay. So when you have two gears engaged with each other, okay, you can draw two circles. If this gear is going this way, then this gear must be going this way, right? Yeah. So this smaller one typically drive the bigger one, the pinion drive the bigger one. So N1 and N2, okay, is the number of teeth on each one of here, and R1, R2 represents the radius, right? And omega 1, omega 2 represents the angular speed, right? So in this case, pinion typically less than the gear, so your R will be less than 1. Right? So that's sort of the convention when you have R less than 1, which essentially you get a so-called speed reduction, right? Gearbox. Right? However, in automotive application industry, so if you look at some of the manual, when you talk about gear ratio, they often actually refer to the number of teeth on gear over the number of teeth on pinion. So it's actually R greater than 1. Right? So just bear in mind the context you're reading. Right? So let's look at the gear train property. Okay, so very quickly look at the gear train property. So I'm gonna probably bring the picture out of here. So let's look at this gear train out of here, okay? I mean, literally you can draw 1, 2, 3, 4, 5 circles, okay, and tangent to each other. So that gives you a gear train at here. So some of the notation very straightforward. N represents the gear number of the gear teeth for each one of the gear. Okay. And N2, okay, represents the velocity, okay, the angular velocity. Okay. Now, when you have a gear train like this, okay, there is a value which is called the train value, okay, E at here, that you probably want to calculate. So this is called gear train E at here, and E is defined as positive and negative. It's a ratio. The numerator is called the product of driving tooth number. The denominator is the product of driven tooth number. Okay, so that's how the train value E is defined. Okay. So let's take a look at, for this particular example, what would be the E value, right? Okay. So if I use this formula here, let's look at what's the product of driving tooth number. So what you need to find is which gear can be categorized as the driving gear. So this must be a driving one, right? So this driving 3, and 3 is driving 4. Okay, and 4 is not driving anything at all, but 5 is driving 6. So basically, the product of driving will be N2 times N3, and then times N5. Okay, so that's product of driving one, and the product of driven. Now the 3 at here is not only a driving one, but also a driven one, right? So that's N3 at here again. N4 is a driven one, and N6 is a driven one. Okay. So this is the E value. What about the positive and negative? So positive and negative you add it on to look at the direction of the input and direction of the output. If the direction and output changes from the input, then you put a negative here. And in this case, the two directions are different, so you do have a negative value. Okay, so what this E does is your output angular velocity basically equal to E times input angular velocity. Okay, so that's what this E does. One other thing on the side note is a very special gear within the gear train is number 3. So number 3, we call that an idler gear. Okay, so basically the idler gear will feel both driven and driving force. Okay, so it's in the middle of the 2 and 4. Okay, usually idler gear functions in 2 ways. One way is idler gear changes the direction of rotation. Okay? And the other way is, it's also very important in application idler gear is, let's say for example, right? If you have a shaft here and here, okay, and you have a gear 2 and a 4 already designed, but you don't want to change the location of the 2 shafts. So basically you don't want to make it closer or make it far away. So then what would you do if you still want the power inputs to be outputted here? Then you need an idler gear in the middle, right, to transmit the power. Okay, so that's basically another application of this idler gear. Okay. You can use idler gear basically to adjust the spacing between 2 adjacent shafts. So that's gear train. Okay, a more typical structure of gear train. You can look at this is basically example. This is a 2-stage reduction gearbox. Okay, you can use similar formula to calculate the train values if you have all the necessary parameters. So that's gear train. Now let's look at the gear force. This part is very, very important because it's directly related to the next stage of a shaft design, which in parts we kind of already done it in some of the exercise before the midterm. Okay? Because shaft will carry different component. One of the component it can carry is a gear, right? So you do need a shaft to carry gear and transmit the power. So, and in this case, let's look at the gear force for spur gear first. Okay. So when you have a spur gear, you can draw 2 circles, 2 pitch circles representing the 2 gears. Okay. And you have the relative rotation like this. And that's the pitch line. And then you have, okay, the line is not drawing properly, it should pass this. And then you have the line of action like this, right? Yeah. So the action-reaction force, okay, when 2 gear teeth are engaged with each other, will be along this line of action. All right? Yeah. What you can do is you can draw a free body diagram. Let's say I'll draw the free body diagram. This is, I suppose I should draw exactly the same size, right? But let's draw it slightly bigger here, okay? Okay, so if I have, this is a pinion in here. In the middle is the location of the shaft. So the pinion, let's say, rotate this way. And now the pinion, of course, is driving the gear, and the gear is going against the pinion reaction force. So right at this pitch point, you would have a reaction force, right? We call that W, coming back from the gear teeth. Okay. And this W can be decomposed into the horizontal and the vertical component. The horizontal one we call it WT. The vertical one we call it WR. Okay. And WR is the one that actually basically goes through the center of the gear or the shaft. Okay. WT is the one that's horizontal. So guess what? The WT is the one generating or because of the torque, right? So the horizontal WT times the radius gives you the torque. Actually, by the way, in the midterm, I can remember that a lot of students, when they calculated the torque, I don't know why, but in the diagram, it specifically listed a radius equal to 100 millimeter, right? Because there's so many of you, again, you divide that radius again to time the force to calculate torque. So you end up with basically half of the actual value, the torque, right? Yeah. Just have to read it carefully. So this TA should be W times this. And to make it balance, okay, because of W, so then you need a force from the shaft, okay, to balance out this W at here. So this is essentially the free body diagram for the pinion, and you can draw a similar free body diagram for the gear. Okay, same thing. Okay. Most important parameter right here, okay, are these three parameters. So we call WT, okay, we call it a transmitted load. We call it as a transmitted load. And WR, and we call it radial load. So radial load doesn't generate the torque. So it's the transmitted load that will generate the torque, or because of the torque. Okay. So if the diameter is D, okay, so apparently your WT times half of the diameter will be the amount of the torque at here. Okay. So that will be the torque. And then suppose the pinion is the input shaft. So we'll look at this a little detail again. So you have a certain input power, it's called H, right? So H will be basically the torque times the angular speed omega. Okay. So which is WT times D over 2 and times omega. So just be careful, my writing is a little bit confusing. This is W, this is omega, right? It's kind of hard to tell. Make sure you understand the difference in notation in here. Okay. And of course, you can always basically derive the relationship between WTW and WR. As you can see, basically WR equal to W times cosine phi, and WT equal to W times sine phi. Okay. And in this particular case, which we'll notice for our next gear, okay, we'll have another notation called the WA. It's called axial loading. So it's the loading along the shaft. Okay. Right. So in this case, it's a spur gear. So you're not going to have any axial loading. Okay. But the next, when we look at the helical gear, we'll see that the WA will not be zero anymore. Okay. Yeah. Okay. That is spur gear. Okay. So now let's look at gear. Let's look at helical gear first. And then we'll look at the gear force on helical gear. Okay. So this is where the handout that I gave it to you come in handy. So this big handout here has quite a few terminologies related to helical gear. Okay, so let me go over this, okay, with you. So again, when it comes to terminology, it's very hard, especially the first time. It's very hard to memorize all of these different terminologies. There's just so many, right? But it's okay. You just have to practice a little bit, and then it's not that difficult. It's not like solving an integral or anything. Okay. First of all, we have introduced helical gear. Okay. Helical gear is the type of gear that the gear tooth, okay, is not straight. Okay. Which is basically means it's a part of the, if I have a cylinder, okay, then you can always generate a helix or helical curve around this cylinder. And helical gear tooth basically is, the profile is a part of that helical curve. So that's basically what this part of the curve is all about. Okay? And because of this, and when you look at this in two different perspectives, you're going to have basically like a two set of parameters. So if I look at the front view, which is the AA cross section, so that's where you look at it, right? You see that? That's basically exactly like what you see for spur gear, right? Okay. And if you look at the section view in the BB, okay, and the BB is not sectioned arbitrarily, right? BB is sectioned using the so-called the helix angle. Okay. So what's the helix angle is when you have a helical curve, okay, and if you pick any point, you draw the tangent vector, okay, along that curve, and if you measure the angle between this tangent vector and the vertical axis, okay, so you basically measure the two angles between these two vectors, then you get the so-called helix angle. Okay. And this helix angle is how you section this gear using this BB section. Okay. So you have this view from this perspective, okay, using the helix angle. For helical gear, helix angle is not a set number like a pressure angle. Pressure angle, we have a set number, right? 20, 25, you can choose yourself. But helix angle, you can actually choose between 5 to 30, typically with a 45 degree as a maximum angle. Okay. Sometimes if you look at gear catalog, okay, they probably already manufactured according to certain helix angle. Okay. So if you look at from this BB perspective, then you have a view like this, which is basically exactly the same kind of view like A, right? So pretty much like you're saying another set of spur gear. So, but okay, you do have a two set of parameters now in these two different views. Okay. So what are the two different parameters? For example, the diametral pitch. Okay. Diametral pitch for spur gear, you have only one diametral pitch now. But for helical gear now you have two diametral pitch. One in this view, we call this is transverse view, and the other view is this the A is the normal view, and B is called the transverse view. So in these two views, you have two different diametral pitch. Okay. So this is where I'm going to write down some of the parameters, okay, just to indicate the difference between the two different views at here. Okay. We use small letter P for circular pitch, but now I have a subscript small t. So basically this will be the transverse circular pitch. And then you have a small p with a subscript n. So that will be the normal circular pitch. Okay. And these two are related with the helix angle. So small pn equal to small pt times cosine helix angle phi. Okay, and that's actually quite easy to be identified from here. Okay, and by the way, the section view from this one is from a helical rack. Okay? So this is a racket here instead of a circular gear, right? So this is a rack. Okay? A rack is when the radius of this becomes infinite. Okay? Another thing is so-called the axial pitch. So axial pitch refer to the distance from between two corresponding points along this axis of rotation. This is basically from A to D. So you have this so-called axial pitch. So we use px, and px equal to pt over tangential helix angle. Okay? And then capital P and capital PT, capital PN, they're the so-called transverse and normal diametral pitch. So let me write down here, so we're almost done here. And capital PN is equal to capital PT over cosine helix angle. Okay. And similarly, the pressure angle also has two sets, one in the transverse plane, one in the normal plane, phi t, phi n. Okay, they are not the same. Always remember the pressure angle, they are not going to be the same, and you can relate this using this formula here. Okay, so that will be the last one I can write. All right. So anyway, so that's pretty much this portion. Any questions? Okay, we'll see you on Wednesday.